I'm Mary Turner, Director of Training here at Brough Research, and I'd like to welcome all of you for attending. And from looking at the list of attendees, there are some of you who have attended some of these presentations in the past, and to some extent, this webinar is based on feedback you've been giving us as a result of some of those webinars in the feedback form or from getting in contact with us afterwards. So what we're going to talk about today, and what's sort of in the name, in the title, is a lot of the feedback we've been getting is that you're interested not only in how Apex works, of course, but also how to use Apex. Because when you work in Apex, and we talk about the four-step process, the design and verify the geometry, design and verify the sources, trace the rays, and do the analysis, you know you're getting the correct answer to your question, but it's not always easy to make sure or to understand that, am I really asking the right question, and what is the information actually telling me? So that's part of what we're going to talk about today. And to do that, what we're going to do is to take a somewhat brief look, as much as we can do within the time frame allotted, at radiometry primarily, a little bit of photometry as well. And we are going to spend some time looking at the terminology, because to be perfectly honest, the terminology can sometimes be the most confusing part of the whole analysis process. And then what we'll do is look within the Apex environment at looking at how we analyze the radiometric quantities, and then again put them into the perspective of what is this data telling us. So let's talk briefly about radiometry and photometry and what the differences are between them. And as I'm going on and on, you will notice you all have a little chat box available to you. I'm not going to be answering your questions during this presentation, but there are a couple of people who are online and listening, so they can potentially answer your question in real time, or if we need to wait until I'm done, we can capture all of those questions and we will get back to you with your answers later. So just use your chat box anytime you have questions or comments. We look forward to hearing from you. But to continue on our discussion, sort of a brief overview of radiometry and photometry. The fundamental difference between radiometry and photometry is radiometry is interested in all the energy. All electromagnetic radiation, and radiometry is simply the process of measuring that radiation, and it covers light of all wavelengths or of all frequencies, whichever space you prefer to think in. So when we talk about the optical spectrum, we sometimes talk about 0.1 to 1,000 microns, but effectively it goes from 0 to infinity, although neither of those numbers make sense in frequency space. So when we're talking about radiometry, we're not only talking about visible light that the eye can see, we're talking about ultraviolet radiation, infrared, and well beyond both of those in shorter or longer directions. When we're specifically talking about photometry, which is a very important parameter when we're doing illumination system design, because typically we're designing systems for which the human eye will be the detector, photometry is a special form of measurement that only takes into account the light that can be detected by the human eye. And then we further weight that by the response of the human eye. And of course, the human eye response varies as a function of the lighting environment, the photopic, scotopic, and mesopic regimes. But fundamentally, we talk about light having visible light being from approximately 360 nanometers out to 830 nanometers. And yes, I do speak in nanometers and type in microns, but I'm sure you can all make the conversions. Just a tick I've picked up over the years. So let's take a look at some of the quantities we're dealing with when we talk about radiometry. When we talk about radiometry, we're talking about real energy based on the energy in a photon of light. So in radiometry, we start at the most fundamental level, the radiant energy, or the joules per photon. Goes right back to Planck's law. We start with the photon emits energy, and what do we do with that energy, or what happens to that energy as it passes through time and space? One of the key parameters we're always interested in is what's referred to as radiant flux or power. And you'll notice the radiant is in brackets. I said I would be talking a little bit about the terminology. When we simply say flux, it's going to normally be assumed we're talking about the radiometric quantity. Typically, if you're talking about photometric quantities, you're going to specifically indicate those with special terminology. And again, as I said, terminology, nomenclature is one of the most difficult aspects at times. So you don't always have to say radiant flux. You can simply say flux, and radiometric quantities are typically assumed. But in all honesty, if you want to make sure that people know exactly what you're talking about, I would recommend using the prefix of the radiant. And again, power is also simply often used. And when we're talking about power, we're talking about watts, what comes out of the wall outlet, if you want to think of it in those terms. And based on our fundamental quantity of the energy in the photon, watts is simply joules per second. So how much energy per unit time. Now we'll talk about some of the other parameters that you're going to be interested in when you're doing a radiometric analysis. And again, it can have multiple names. Irradiance, or radiant incidence, or radiant excitance, also called flux density. When we talk about radiant incidence, it's typically indicated with the letter with the uppercase E, radiant excitance with the uppercase M, and excitance is the amount leaving a surface, or if leaving our source, a surface area on our source, and the incidence or irradiance is what is being captured or received. And it's an area distribution, and typically we're talking about watts per meter squared, or often in our designs, watts per millimeter squared. That tells us about the area distribution. What is the power over a limited area? Sometimes what we're more interested in is at what angle is the light traveling. And this is what's referred to as intensity, or radiant intensity. And this is watts per steradian. So what is the solid angular subtense of a particular energy distribution? And the final parameter we'll talk about is radiance. And radiance has information about the area as well as the angular distribution. So it's our watts, our power, per meter squared per steradian of solid angle. So again, just a little bit of terminology. I'll be using those same words when we go through some of the analytical processes. So have that back to refer to. And after this presentation, you'll be able to download this file if you are interested. So what does this all mean, and how do we apply it to the analysis we're trying to do of our system? And I'm going to say illumination system, but it could be an imaging system or any item that you're trying to analyze within the APEX environment. What I want to talk about is the basic process of transferring radiation, transferring energy. Let's assume we have some small area on our source, and I'm going to call that DA1, and I drew something large enough for you to see, but of course we can shrink these down to infinitesimal size if we want in the limit. And then we have some small differential area DA2 on this region I'm calling my detector. And they may be aligned normally to each other or not, but they're aligned at some angle, theta 1 and theta 2 relative to their normals. And they're separated by some distance s. What we're trying to determine is how much of the energy that is emitted from this differential area is actually going to be captured on this target, this detector. Right now, it's a simple system, source and detector. Obviously, in the real system, we're going to have many other components involved, mirrors, lenses, etc. But we can still think of it at this very basic system. So we can look at it mathematically, and we can calculate how much energy from this differential area A1 is captured on our detector by simply integrating over the two areas involved, the radiance divided by the square of the distance, and then the projected area of the source as seen by the target, and the projected area of the target as seen by the source. This particular equation is what's referred to as the fundamental equation of radiative transfer. When you're doing illumination design, illumination analysis, this is the equation you're trying to solve. So let's think a little bit more about what that equation is telling us. It simply tells us that the power captured on our detector, which I'm referring to as dA2 here, is a function of the power coming from the source, the radiance of the source, the size of the source as seen by the detector, the size of the detector as seen by the source, and the distance between them. And those are all, again, for our simple system, parameters we can readily understand and indeed measure. So let's look at a very, very simple example. Let's say I have a collimated source. Okay, I bought it at the point source store, so it has an extended area, but all of the light is leaving perfectly parallel, directed along, in this case, the z-axis. And somewhere downstream, I have a target that's the exact same size as my source. Okay? Because I have perfectly collimated light and the target is the size of the source, every single bit of that energy, which I'm representing here with this limited number of rays, is going to get captured at that location. And we're going to have the same amount of energy in each of these little differential areas, dA1, dA1A, dA1B, etc., however you want to think about breaking it down. And all of the rays are still going to have a direction vector in the z direction because we've done nothing to change it. And again, this is let's assume this is an ideal lossless environment, as we typically do when we do these types of calculations. Now, if I change things a little bit, let's say I give the source some amount of divergence. So the rays will be traveling out at some angle within a forward hemisphere. If I keep a target of exactly the same size, then obviously some of those rays, because of this traveling distance, are going to miss the target. And in this particular case, and I believe I just put like a 10-degree divergence here, not quite sure. It was either 10 or 30 degrees, but we could reverse calculate it. We see that only about 86% of our energy makes it to our target, rather than 100% of the energy. Now, I can expand the size of my target to such a point that all of the energy gets captured. I can do that. But in both instances, I'm going to have changed part of my results. In the case of the enlarged target, I did capture all of the energy, but over a larger area, which means the area distribution over the little differential areas on my target will now be slightly different than they were on the source. Okay? And the energy is still going to be traveling at the same direction when it reaches the target as it had the source, because again, we're just traveling through this ideal lossless media at this point. No lenses, no mirrors, no gratings, etc. But we're going to put those in. Okay? But again, things have changed slightly. And sometimes that's what we need to know. And of course, we could add more complexities. So in this particular case, what I've got is diverging light. And I have tilted, I actually have tilted both the source and the target relative to the system normal. And I can again capture, and I did this within Apex, how much energy is actually reaching this target from this source. And to be perfectly honest, if I had wanted to, I could have calculated this, I'll say by hand, but as we all know, I probably would have been into an Excel spreadsheet or a calculator, but it's a calculation that can be performed. Okay? The problem is once our systems become a bit more complicated, When we add multiple components, more complex shapes, for example, faceted reflectors, Fresnel lens arrays, you can't really do a hand calculation and get the answer. And even in that case, for most simple cases, I can get the total power that reaches a particular location, but understanding its distribution in area or angular space is a lot more difficult. And typically, in addition to total power, I do need to know the positional and the directional information. And sometimes I need to know or want to know both simultaneously. Okay. So now let's take this back into the context of our radiometric definitions. And I'm going to start with radiance. Although it was the last item in the table, in many ways it's the most important parameter that we might be interested in because it contains all of the information. It tells us not only about the area distribution of the energy, but it also tells us that about the direction that light or that energy is traveling when it reaches that surface as a function of area. So it's power per unit area per unit solid angle. So it's going to tell us how much of the power emitted from our source, in this particular case I'm talking about our surface, will be, our little dA1, will be received within the projected area of the target within some viewing angle in a three-dimensional environment. So the solid angle of the source as seen by the detector and vice versa. Okay. So again, it's the fundamental quantity in radiation, in radiometry, because it does have all of the information we need. Once we know what the radiance is, we can capture any other piece of information that we need. So here's the basic definition of our radiance, and it's a function of our power and our projected area, as well as our solid angle. And again, typically in watts per meter squared per steradian. And if I integrate the radiance, overall area, and solid angle, I get the power. If we talk about radiant intensity and the irradiance, the radiant intensity is the power emitted or received per unit solid angle into some specified direction. And we can think of it as the power per unit solid angle, or if we started with the radiance and we integrate the radiance overall area, we will also get our radiant intensity. If we talk about the irradiance, either the radiant incidence arriving or radiant excitance leaving, it's the power per unit area at the surface. And again, we can think of it in terms of it being the area distribution of the power. So the power per square millimeter meter, for example. Or again, if we have the radiance, we can integrate it over all angle space to get the incidence or irradiance. Okay. The important part to consider is, or to remember is, when we calculate intensity, we're throwing information away. We no longer know where the energy is landing. If we determine the irradiance, what we've thrown out is all information about the angle that the ray is traveling at. So although these are very important and useful parameters, we have to understand that when we calculate these, we're throwing some information away. And that's sometimes where people have questions about what exactly the analysis means. And that's what we're going to be talking about for the rest of our presentation here. The last item, of course, is our power, or radiant flux. So the energy per unit time, either leaving or being received at a surface. This parameter simply tells us how much there is. It doesn't tell us anything about where it is, what the distribution is, what the directionality is, simply how much there is. Again, a very useful parameter, probably the first question you want answered when you start your analysis, because obviously if you're not getting enough power to your target location or your location of interest, there's no point in doing much more analysis because you're going to have to go back to the beginning to get more power to where you're trying to get it before you worry about exactly what the distribution is. So those are some of the basic parameters of radiometry. And very briefly, I'll touch on photometry. Most of the analysis we'll be doing today will be radiometric, simply due to the time limitations. Photometry, as I mentioned, is simply a normalized form of radiometry. Photometric quantities are very similar to the radiometric quantities, but again, they've been weighted relative to the response of the human eye. So when we talk radiometrically, we're talking about integrating over all possible wavelengths, 0.1 to 1,000 pretty much. Micrometers gives you pretty much all the energy in most instances, but again, theoretically, it's all wavelength space. But when we talk about photometric power, we're only talking about that from 0.36 micrometers to 0.83 micrometers. And again, we're going to have the weighting factor to take into account the responsivity of the eye at each of those wavelengths. Photometric quantities, again, take into account the human eye. And if we're talking about photometric quantities specifically, we want to make sure that we somehow indicate that. And typically it's with something that refers, it is luminous or illuminance, something that is related to the word lumen is typically there. So we'll talk about luminous energy, luminous flux, illuminance or luminous flux density, luminous intensity, and luminance. And each of these, of course, you can see correlate in some way to our fundamental radiometric parameters. But let's start in this case with our luminous flux, which is measured in lumens. To keep a consistency with our radiometric quantities, that required the definition of a unit often referred to as a Talbot, that is a lumen second. Why? Because when we're in photometric space, we're not bringing things back to a fundamental property of physics, the energy of a photon. We're creating a relationship. So we have to sort of create units to make it work, just to have this, again, sort of a correspondence between photometric and radiometric units. Looking at illuminance or luminous flux density, this is, again, think of it sort of as power per area, but instead of radiant power, it's going to be lumens per area, so lumens per meter squared. The parameter lumen per meter squared is often referred to as a lux. So when you talk about an iso-lux plot, you're talking about plotting the data in lumens per square meter. Luminous intensity is the solid angular distribution of the luminous flux. This is referred to as a candela as well. Candela is in many ways the base unit in photometry because the candela is one of the SI base units. So the ampere, Kelvin, kilogram, second, meter, and mole, and the last of the SI base units is the candela. And then we have our luminance, the photometric equivalents of the radiance, again, our lumens per area per solid angle, or since this is our candela, we can talk about this as a candela per meter squared. As I mentioned when we started, sometimes the units is the hardest. Understanding what the units mean is the hardest part of radiometry and photometry. And I will say that I typically stay to the definition rather than the terms, obviously lumens, but I'll stick to lumens per meter squared just because there's often an difficulty or making sure everyone understands the units that we're specifically talking about. And sort of a generalized depiction. I have a source here, and it's a candle because we know candles not only provide light, but candles also provide heat. And heat is a form of radiant energy, but that heat energy is typically not seen by the human eye. So when the light leaves, and we'll talk about light going into some solid angle, so energy into a solid angle is our intensity, and then somehow it gets mapped into the human eye. Only part of that energy is actually going to make it through the pupil of the eye to be imaged by the eye or to actually activate part of the sensor system in the eye. But this would be power per area per solid angle, so that would be our luminance. So although the candle itself, the output of the candle is illuminance, and if I had an appropriate detector here, I could capture all of that energy, or the energy within this solid angle. The human eye will only detect a subset of that. So another area of confusion sometimes is converting from lumens to watts. As I said when I started this discussion, when we talk about watts, we're sort of talking about what comes out of the wall outlet. Okay? Watt is a measurement of power used. It does not tell us anything directly about how much visible light is output. As we all know, we can plug things into the wall and turn them on, and they produce no light at all. My blender doesn't produce light typically. My light bulbs do. But when we talk about watts, it's the total power used, which means it's going to include things like heat losses. Now, yes, other devices have heat losses as well, but heat loss doesn't help us in terms of light energy from a particular source. It's also going to include that light. For example, if I plug in an incandescent bulb, halogen bulb, I'm also going to get infrared and ultraviolet radiation. I'm going to have, again, heat losses, that some of that is converted to heat. But again, it's light that the eye does not respond to. When we talk about the lumen, it is simply a measure of visible light. And again, we're talking about the 360 to 830 nanometers. There is no direct correlation between lumens and watts. Okay? If I have a 100-watt incandescent bulb, it's not going to produce 2 times the visible light as a 50-watt incandescent bulb. And indeed, we can have several different 100-watt incandescent bulbs that produce different amounts of visible light just because of their manufacturing process. So don't try to directly convert from watts to lumens. If you're interested in how you do that within the Apex environment, there is another webinar that I did on that subject that you can go up and take a look at. But we're not going to go in and repeat that as well. But again, no direct correlation between lumens and watts, but you can ask Apex to calculate it for you. The parameter we're typically interested in is what's referred to as luminous efficacy. The candela is the luminous intensity, so into some given direction of a source that emits monochromatic radiation of a frequency of 540 times 10 to the 12th hertz, and it has a radiant intensity into that direction of 1/683 watts per steradian. As I said, the candela is an SI base unit, and that is the base unit definition. I speak usually in wavelength space, not frequency space. So this is our 555 nanometers, 0.55 micron wavelength. The luminous efficacy is the ratio of the luminous flux output to the input power. So it's lumens per watt. So it's the amount of visible light you get as a function of the input electricity. Maximum possible photopic, so bright response of the human eye. Luminous efficacy is 683 lumens per watt for monochromatic light at this particular wavelength. The scotopic maximum is 1700 lumens per watt, so that's in the dark environment, but that's at a wavelength of 507 nanometers. So this was all sort of to get you comfortable, I hope, with the terminology. Now let's take it back to what happens in the apex environment, where we're going to do, again, define our geometry, our sources, trace rays, perform analysis. So how do you solve that really, really nasty double integral? But I figured since we're presenting this webinar live on a Wednesday, you've recovered from last weekend, you're not thinking about next weekend yet, so your brain should be ready to deal with double integrals today. How do we solve them? As I mentioned, for simple cases like this, those square or rectangular planes, things like that, we could actually do the calculation ourselves. But for real systems and even for simple systems, we're probably going to let Apex do the work for us. Okay. We use ray tracing basically to model the source energy as it emits from the source. What we say is each ray represents one of those little differential areas, and it has a differential amount of the energy. In the sum, all of the rays totaled up to the amount of energy that's actually leaving the source. When the ray propagates, the radiance of that ray is conserved, again, assuming an ideal lossless medium, like air, we typically treat that way. If the radiance of the source is known at any location, that can be at the source, that can be at some aperture or output location in our light train, but if we know what that radiance is anywhere, then we can calculate it everywhere. Now, the one limitation to this is the overall accuracy of our simulation is determined by the number of rays we trace. If we don't trace a sufficient number of rays, and statistically we can determine what that number of rays should be, our results will be inaccurate. But we can typically start by tracing a modest or moderate number of rays, and as we get closer and closer to our final design form, then we would increase the number of rays to get the accuracy required for our particular simulation. But if we want to think about it at its most basic level, Apex was created solely or almost solely to solve the fundamental equation of radiative transfer. So let's talk about the calculations that we might want to make. One is the incident power, the total flux on our detector of some area from our source. And in reality, we're now not just going to talk about area A2 and A1. We're going to integrate over all the detector area from all of the source area. And again, it depends upon the distance between the source and the detector, the angle between the source normal and the detector, and the angle between the detector normal and the source. And voila, it takes us right back to our fundamental equation of radiative transfer. So the total power on the target is the sum of all of the energy seen at all of the points on the target from all of the points that make up the source. And ray tracing is simply a numerical solution to the integral. The integral cannot be solved in closed form typically. We have to apply sort of a trapezoidal rule type approach, and we do that via ray tracing. So let's take a look into Apex and let's look at some of the calculations that we can perform so you can get an idea of what's actually being calculated or measured when you perform a particular type of analysis. And I'm going to start with a very simple case with a very well-known outcome. I'm going to have a parabolic reflector with effectively a point source at the focus position. So here's what it looks like. Here is my parabolic reflector, has a focal length of 25 millimeters, located at the focus position, so 25 millimeters away, is a tiny spheroid that I'm going to treat as my source with a 1 millimeter radius. And again, effectively, that's a point source. So what I'd like to do now is take a look at the ray trace. And so here's the system set up in the Apex environment. And let me pick my little 3D mouse here so we can zoom in. And I'm going to change the, change the transparency so we can come on in. And there you can see the source at the focus position. Okay. So I have already done my ray trace. So what I'm going to, let's end that. So what I'm going to do is bring back that ray trace. And I'll just come right over here and activate the ray trace. And here's the result. And we can see the energy on the detector. And we can calculate that information. So if I simply come over here and select my target area, if I wanted to come up here and just say summary statistics, it's the quickest way to get it, it tells me that about 92% of the energy actually reached my target. Now, how did my energy reach the target? Well, I can analyze that as well. And there are 3 possible ray paths. And we have the energy that leaves the source, hits the reflector, emerges all but collimated, and therefore hits the target. And that was about 89% of the total energy. We have some of the source energy that leaves at a small enough angle to be captured by the target, but not a large enough angle in the forward direction to actually hit the reflector. And that was about 2.5% of the energy. So if we add those up, there's our 91.5% of the energy, rough numbers. But we also had those rays that were leaving at an angle so small they missed the reflector, but so large they missed the target. And that was about 88.5% of the energy on the target. Okay. So now we know how much energy made it to the target. Now what do we need to do? What are the other pieces of information that might be of interest to us? So if we look over here on the Analysis tab within Apex, we see a couple of options. And right now, I'm just going to look at 2 of them, the irradiance and the radiant intensity. The irradiance is going to give us the power per unit area across the surface I've highlighted. And the radiant intensity calculation in cosine space will create a plot in direction cosine space, and it will effectively give us the power per unit solid angle. So what the intensity I'm going to start with irradiance. What the irradiance calculation tells us is what the distribution of energy looks like across the surface. And yes, I should probably go in here and average this a little bit. And let's make it look real pretty by doing some radial averaging. Should have traced more rays, and now I have that data, and we can see. And what this allows us to see is that we have a nice rotationally symmetric distribution of energy, as would be expected. You'll notice that it is effectively pixelated, because when we do the calculation, we have the ability to define a data resolution, and I chose 101 by 101 pixels, square target, aspect ratio is equal to 1. So you could do the math to figure out what size each of those little pixelated elements would be and get an idea of how much power went into each of those. But it doesn't tell us anything about what angle or what direction the light is traveling in. Now, in this particular case, we sort of know the answer to that, but we have thrown out information about angle. So if I want to know about the intensity or how the light is traveling, not where it landed, but how it's traveling, I can do that using an intensity calculation. And I'm going to look at the intensity in cosine space. And I've already done the calculation, but I want to pop up the dialog just so we can take a look at it. And you'll notice that I have an ability to convert it over to angle space. I don't know about you, but when I see a direction cosine of 0.5, I don't think I have a direction cosine of 0.5. I think, oh, that's 30 degrees. That's sort of how my mind thinks, and more often than not, I do work in angle space. So this calculation can do that directly for me. And I can choose to set a range of direction limits, or if I were to choose automatic, Apex will scale it based upon those rays that have the maximum extent. But as I said, I've already got this calculated, so let's take a look at our intensity calculation. And you'll notice we have a very, very bright peak right here at the center. But you'll notice the width of the box in direction cosine space goes out to about plus and minus 0.29. Why? Because we have those rays that didn't hit the reflector that are hitting all across the target. So in many of these little areas here, there is some energy. It's just the maximum ray went out at one of these corner positions. But most of our energy is traveling out within a range of direction cosine space between minus 0.01 and plus 0.01 in the A and B direction space. And I know that because I had 101 pixels. So that's the width of each of those pixels in direction cosine space. Okay. So that's how this size was determined. But again, as we know from our simulation, point source at the focus of the parabola, the light that hits the parabola comes out collimated. Now, there's not a whole lot more we can do with this particular simulation because it's extremely contrived. But what we want to do is understand what these are telling us. What this is telling us is what the distribution of energy is over the surface, and that's it. That's all we know is what the power per area is at each of these individual pixels, and you can read that value over here. Or you can export this data, for example, as an Excel spreadsheet and bring it over to Excel. And in this particular case, we just know that most of the rays are landing effectively with a direction cosine of 0, plus and minus 0.01 for the bin size. But we don't know anything about where the energy is. Sometimes we need to look at other information. Sometimes there are other types of analysis we need to do. And to do that, we need to complicate the system slightly. And that's what I'm going to do. And my initial complication is going to be pretty simple. Let me close this one. No. And what I'm going to do here is I'm simply going to take my point source and I'm going to move it a little bit. So in this particular case, I have exactly the same geometry, exactly the same source, but I've now offset it closer to the parabola, but still far enough away to be considered fundamentally a point source by about 5 millimeters. Okay, by exactly 5 millimeters. And I'm going to look at a ray trace. And again, we're going to get effectively the same result. About 89% of the energy is going to go from the source, hit the reflector, and then hit the target. About 2.5% is going to leave the source and hit the target. And about 8.5% is going to exit the source, miss the reflector, and go off into space. The key differential is we don't have collimation. You can notice by looking at these rays, and yes, we're looking at a two-dimensional projection of three-dimensional space, but you can see these rays are definitely not collimated. You can see the little kinks in it. So how does that affect the results of our, excuse me, how does that change affect the distribution of energy at our target location? And again, let's take a look at it in that space. I do have the ray trace already here, so let's activate my ray trace. And here we go, and we can see the rays going off into space, and we can look at it in this orientation. And you can see this ray is somewhat collimated, but not really. And we definitely see that this is not collimated light. So how does it affect the energy on the target? Now, even just looking at this limited number of rays, you might start to think you're seeing something. And again, let's take a look at the irradiance. And I'm going to use my same resolution of 101 by 101. And we'll take a look at the irradiance. And again, I've already calculated these, so let's take a look at the irradiance. And here's what the irradiance looks like. Now, it says that we have a particular zone that is, and we can use our cursor, but we know that each of these pixels, because we have 101 pixels across 300 millimeters, let's call it 100 across 300. So each of these is about 3 millimeters thick. So we have a zone that's somewhere around, say, 10 millimeters thick, where most of the energy is reaching the detector. Now, I don't know how well this is projecting through space. I can look at this and I can see, and you can see down here a little bit more information. But what I want to do is to make it a little bit more noticeable. So what I'm going to do is just modify the data slightly. I'm going to look at it in a logarithmic scale. And let's use 2 decades. So I have this new data set, and so here's what it looks like. So you can see that all of the energy isn't landing in this zone, but most of it is. And you'll notice that there's very little landing right at the center. Okay, so again, let's look at these two together. So here is the data in linear space, and here's the data in a log space. So now let's take a look at what is the intensity distribution. At what angle are the rays incident on this surface? And again, I'm going to go to my radiant intensity calculation. And again, we can limit it to the range of all of the rays that are being captured on the target. And let me take a look at that there. And there's what the data looks like. And in direction cosine space, it's about plus and minus 0.28, effectively almost the same as it was previously. And we see we have a narrow zone here where no energy is reaching the target. You'll also notice right around an angle of 0, the pixel where all of our energy was in the previous simulation, it's now totally empty. Why? Because I don't have a point source at the focus of a parabola. So none of the rays are being collimated. The only light that can possibly hit right here would be a small number of those rays leaving the source that actually were coming out collimated by definition from the source. So again, we wouldn't expect to see anything there. Now, just as an aside, when we come up here and we did radiant intensity, I didn't in this case, but remember I mentioned previously you could also convert it to angle space. And I didn't mean to do that one, but that's okay because that's what it would be out to 90 degrees. So I'm going to delete this one temporarily. Okay. There also is an option to do a radiant intensity calculation in angle space directly. And if you're working in angle space, then this might be a preferred option. If your source has a distribution, or if you're looking at something over a hemisphere, you definitely need to use this calculation because it will allow you to do things in a spherical polar coordinate system, but you can capture data over up to a sphere. As some general comments, which do you want to use and why? When we do the direction cosine data, the data is going to be captured into bins that have an equal width in cosine space. So in our particular case, when I did this 101 by 101, each bin has a width of about 0.02, again, in direction cosine space. As we know, a sine function is not linear, but out to about, say, 30 degrees, we can treat it as linear. So if we convert from direction cosine space to angle space over a small range of angles, we're not going to have much error. But if we have much higher angles, if we go beyond a hemisphere, then we really should be mapping the data into angular space. It's up to you to determine which method is appropriate for your simulation, but again, the tools are available to you. And in this particular case, here is the radiant intensity converted to angle space, and here is the direct calculation in angle space. Didn't quite get the, oops, sorry, wrong. Got to grab pictures if I want to duplicate them. Resolution isn't quite the same, but close enough. And you can see that in this case, the data is effectively the same, so it doesn't matter. Right? But what do we want to do? We want to try to, in our mind, understand what these calculations are telling us. We want a correlation between the data, a relationship between where the data landed and how it got there, combined with how much is there, the power. We can look at these and say, okay, we can pretty much guess that the rays that reached out here were traveling at this angle. But how do we find out how much that was and any other type of information we're interested in? So this is where we would do what's called the radiance calculation. The radiance area calculation allows you to divide the target into small areas, and then you can query each of those areas as to how much energy landed within some range of angular space. Okay? So let's take a look at our case, and in our situation, we obviously, with our target plane, only need to sample up to a hemisphere, but again, the calculation can go beyond that. Let's take a look at the results. So here is my radiance, and in this particular case, I calculated it over all angles, so it should be identical to my initial irradiance data because I'm capturing exactly the same information. At each of these same pixelated areas, how much energy came in at all possible angles. But I'm interested only in the energy in this region. So I can go in and say, and let's see, did it tell me here? Nope, it didn't tell me. Okay, in this particular case, what I did was I looked at the energy that came within a region, those angles between, I believe, 3 and 7 degrees. So you can see that the rays that came out at between 3 and 7 degrees landed at that zone. Again, this is area. This is minus 150 to 150 in millimeter space, but it's telling us about all of the energy at that area that was between 3 and 8 degrees. If I want to find out about the collimated data, that's not the one I want. This is the one I want. In this particular case, what I said was, show me all of those rays coming out at an angle of less than, I think, 2 degrees. So we have some of the light coming directly from the source, and then maybe some of the rays coming that hit the and some of the rays that hit the reflector. But this is outside that zone. That zone is in here. This zone is out here. So these are rays that went off further across out in space, so at a higher angle, still captured by the target, but not in that hot zone. So again, we can see that only the rays that came directly from the source are effectively going to be at very, very low angle. None of the rays that hit the source hit the reflector itself. That pretty much concludes what we were talking, what I wanted to talk about today. But again, what the radiance calculation allows you to do is to isolate the information in whatever way you would like. So again, here's looking at 3 to 7.5 degrees, and we see some of the light in the center as well. So some of the other light that hit the reflector, but we also see most of the energy in that hot zone is within that range of angles. So that's a little bit about some of the radiometric calculations that can be performed in the APEX environment. And thank you very much for your attention today. As I mentioned, we will be putting a copy of this presentation as well as a recording of this presentation up on our website. So if you would like to look at it again, or if you have other questions, you can get in touch with us. Thank you very much for your time and attention.